Okay, so we're going to pick up and take a look at a couple more examples in the 2.7. And I just kind of want to reiterate the fact that when we're talking about derivatives, we're talking about a rate of change with respect to their independent variable. And the independent variable is typically you would see the independent variable, as x. But the independent variable could be time. And so last week we had a little recap and we focused on, the position function, velocity, and the acceleration function. So I want to take a look here at another few examples. But if you have y equals f of x, then a derivative dy dx can be interpreted as the rate of change of y with respect to x. And this rate could be extended to a wide range of topics. And so the difference here that I illustrated, how do we compute the average rate of change versus the instantaneous rate of change? And the instantaneous rate of change is looking at that limit definition, i.e., finding that first derivative. So let's take a look here at a couple of examples. And let's take a look here at problem number 30. I want you to start practicing, so we're going to do a pause here. So one, I would like for you to find, so when I say find, so you're going to find C prime of Q, and then we're going to interpret what this meaning is, and we're going to do a pause. Yeah, so my tablet is something, so I'm going to type it out and then pause it. Yeah, my tablet and this recording doesn't work out, but anyhow, the rate at which the cost is increasing as the 100th item is being produced would illustrate that proper conclusion. So I wanted to take a look at an example of that magnitude. And in the 2.7 handout on the second page, that's where these are coming from, as well as the textbook. And this refers to problem number 30. So let's take a look here at another example here, which is given in problem number 16. We're not going to do all the components to it, but I want you to get an idea of different types of problems. So the volume of a growing spherical cell is determined by V equals 4/3 pi r cubed, where the radius r is measured in micrometers. And in this particular case, let me see, find the average rate of change. Find the average rate of change of V with respect to R when R changes from 5 to 8. And in this particular case here, this is illustrating the micrometers, right? So for 1 micrometer and converting it to meters is what this conversion is. So let's just illustrate part A, and let's just take a look here at this first part. So what this will illustrate, and this is why, it's very important to understand your units. And so for this first one, if we are going to find the average rate, well, the average rate is going to equal, we have to evaluate the volume when R is 8 micrometers. minus the volume 5 all over, and this is going to be 8 minus 5. And that's where the calculation is going to come into of importance. So this is going to be a 4/3. This is going to be pi. 8 to the third power is going to be 5/12. Minus, this is going to be 4/3 pi. 5 to the third is 1/25. And 8 minus 5 is going to give you 3. And so when you do this particular calculation, we're going to factor out the pi when you are doing your calculation. And then in this particular case, you should get something of 172. And practice with the calculation because that's important, right? And if you're not getting these values, then something is going incorrectly. And so what this is going to illustrate here is, a proper sentence. The average rate of change is 172 pi. But what are your units? Well, the numerator represents volume, and in this particular case, right, the volume is going to be the micrometers cubed all over the time, and the time, oh no, misspoke. The volume here is when the radius changes, misspoke, which is going to be these micrometers. When R, when R changes from 5 to 8 micrometers. And that would be for the first part. And finding the average rate of change is something that we were taking a look back, I think in the 1.4 section. Now we're talking about here, find the instantaneous rate of change with respect to R when R is 5 micrometers. So in this part B, that instantaneous rate of change is going to be dV over dr, which also can be written as V prime with respect to R. And when you take the derivative of 4/3 pi r cubed, the 3's cancel, so you're going to get 4 pi r squared. And when you evaluate V prime at 5, then in this particular case, 5 squared is 25. 25 times 4 is 100. And you get 100 pi. And so this, again, sentence conclusion, the instantaneous rate of change of V. So basically, you're writing all of this is 100 pi, again, micrometers cubed per micrometer. And the trash is coming to be picked up when R is 5 micrometers. So all of this needs to be included here. So in this particular case, I would like for you now to take some time and work on a couple of problems. So let's allocate here, do a pause on the video and work the problems. I would say 10 to 15 minutes. And in this case, you have three parts: part A, part B, part C here. And we'll go over this when we resume back at lecture. And then the second one here, only focus on here part A and part C. And then we will check, because this is now going to transition into the related rates, but I wanted you to have some time to think about these concepts.